Now we're still working with the same example as we did in the last video. In the last video, we were able to come up with our objective function in terms of a single variable. So we had p is equal to 21x minus x squared, and we know we're trying to maximize this function. And then we also have the domain of this function. We know that the domain is negative infinity to positive infinity, and that's going to be important here in just a moment. So steps 1 through 4 are really kind of the setup of this problem. At this point, we're ready to start doing the calculus part of this problem, which means we're ready to start finding our derivative, finding our critical numbers, and then once we have that, hopefully finding our maximum here. Regardless of what your domain looks like, we are going to need to find the critical numbers of our function. So we're first of all going to have to find the derivative of our function. So in this case, p prime, we can just use our power rule, is 21 minus 2x. So there is my derivative. My next step would be to find my critical numbers. So think about places where p prime is equal to 0, places where p prime does not exist. In this case, p prime is equal to 0. That would give me 21 minus 2x is equal to 0. And if we solve this for x, we'll have 21 equals 2x. So x is equal to 21 over 2, or if you would prefer a decimal, we could say 10.5 here. Now, I do want to verify that this critical number that we found lives in the domain of our function. Now, in this problem, our domain was negative infinity to positive infinity, so any number that we found would have been in our domain. But I do want you to keep that in mind. We do want to be making sure that the critical numbers that we come up with are actually included in our domain. The other case I need to consider here is places where p prime does not exist. But in this case, p prime 21 minus 2x, that's a polynomial. So I'll just make a note to myself, p prime is a polynomial, so we don't really need to worry about that case. We're not going to come up with any extra critical numbers because of that case. So I have exactly one critical number, which is good, because I want to look at the domain of this function, and I want to think about, do we have an open interval or do we have a closed interval? In this case, we've got an open interval. Now, one of two things is going to happen. If we have an open interval, that means that we have to hope that we have a single critical number, which, hey, we do here. We ended up with x equals 10.5. I now need to, first of all, verify that this is, in fact, a maximum here. So I need to make sure that this is a maximum. Now, in these problems, we can either use the first derivative test or the second derivative test, whichever you're more comfortable with. So if you wanted to construct your number line and say, okay, here's the number line for p prime, here's 10.5, and hopefully show that the left-hand side is increasing and the right-hand side is decreasing, you could go right on ahead and do that. I'm going to do the second derivative test just because I think it helps to get a little bit more practice in here. The second derivative, so I want the derivative of p prime. In this case, p prime is equal to just negative 2. And what we would do for our second derivative test is we would take the critical number that we found, which was x equals 10.5, and plug that into, our second derivative, which is p double prime, p double prime is equal to negative 2. Now in this case, if I try to take 10.5 and plug that in, I'll end up with p double prime of 10.5. There's nowhere for me to plug in 10.5. No matter what I get back negative 2. So let's think about what this is saying then. This says the second derivative is negative 2. Well, the second derivative test tells me that in this case, our second derivative is negative, which means that we're working with a function which is concave down, We know we have a horizontal tangent line, which means we're talking about this point right here, which means, yes, we do in fact have a maximum, which is good. That's exactly what we wanted. So that means that x equals 10.5 is in fact a maximum. So that's awesome. That's great. What I want to do for my last step here is go back and reread the question, make sure that I find all of the pieces of information that I need in order to answer this question. Make sure I'm actually answering the question that's being asked. So I'm going to go back and look at my problem. We said we wanted to find two numbers whose sum is 21 and whose product is a maximum. So we wanted to find those two numbers. And we have the first number. We said x is equal to 10.5. We're still missing the y value, though. We're still missing what is that second number. Now, I could, if I wanted to, repeat most of this whole process and solve. The big difference here is I would solve for x instead of solving for y. But what's nice here is when we have a constraint like this, hey, look at that. Y equals 21 minus x. That actually gives me a way to very quickly solve for y because I already know that x is equal to 10.5. That we just solved for. We verified that we had a maximum there. So if I wanted to, I could just take that number and plug that in for x and say, okay, y is equal to 21 minus 10.5, which is equal to 10.5. So that means that y, in this case, is also equal to 10.5. So we wanted to find the two numbers. Well, there they are. We've got x is equal to 10.5 and y is equal to 10.5, and we've answered this question.